In this lecture, we're going to begin our presentation on frequency response. And frequency response is one of the most important topics we're going to discuss in this course. So at the very beginning, I want to give you a very quick overview of what you should be looking for. And here's the first very important idea. If a linear time invariant system is given a sinusoidal input, then the output will also be sinusoidal. Moreover, the frequency of the output sinusoid is the same as the frequency of the input sinusoid. And finally, you can find this output without doing an inverse Laplace transform. These few facts will end up giving us a tremendous insight into system behavior. While this topic is called frequency response, it's not the response to frequency, it's the response to sinusoidal inputs. So the term is a bit of a misnomer. We'll start by looking at the mathematical foundations of frequency response. So let's start by reminding you of something we learned back when we discussed Laplace transform. When we developed the idea of Laplace transform, we introduced the notion that the everlasting exponential was an eigenfunction for linear systems. So what does that mean? It means that if we put in x of t equal e to the st as an input to a system, a linear system, the output we'll get will be y of t equal h of s times e to the st. So the output has exactly the same functional form as the input when the input is in e to the st. And the relationship between the input and the output in the case where the input is an everlasting exponential is given by the transfer function, when we call this h of s. And we noted that, of course, that this relationship between the input e to the st and the output is dependent upon what value of s we use when we form e to the st. Let me note one thing about notation here. I'm going to denote the output in response to the everlasting exponential e to the st as y sub e. For the study of frequency response, we'll be looking at particular values of s. And the values of s we'll look at are ones on the imaginary axis. So these have no real part. So s equals j omega in what we're going to study. Then x of t will be e to the j omega t. And of course, that particular input will produce an output, which is h of j omega e to the j omega t. Now the input signal in this case can be written as cosine omega t plus j sine omega t, according to Euler. And at any time, e to the j omega t is just a complex number. It has a magnitude equal to 1 and a phase equal to omega t. And let me point out this symbol here indicates that the phase angle of the complex number e to the j omega t is equal to omega t. So please remember that symbol for the angle of a complex number. The transfer function, when we evaluate it at s equals j omega, is also just a complex number. We can denote the magnitude of this complex number using the braces around h of j omega, and we can denote the angle of this complex number using the angle symbol that we just introduced. Since e to the j omega t is equal to cosine omega t plus j sine omega t, we know the response to e to the j omega t must be the response to cosine omega t and the response to j sine omega t added together. We know this since linear systems obey superposition. Since cosine omega t is the real part of e to the j omega t, we know the response to cosine omega t will be the real part of the response to e to the j omega t. The response to j sine omega t, which is the imaginary part of e to the j omega t, will be the imaginary part of the response to the exponential ye of t. From this logic, we know that the response to cosine omega t will be as follows. The absolute value of h of j omega times cosine omega t plus the angle of h of j omega. So you see the transfer function comes into this response to the everlasting cosine in two ways. First, the magnitude of the transfer function, evaluated at the frequency j omega, shows up as the amplitude of the cosine's response. And then the angle of the complex number h of j omega shows up as a phase angle inside the cosine. So what have we learned? We've learned that we can find the response to a cosine input, an everlasting cosine input, very easily. All we have to do is to multiply it by a number. That number is the absolute value of h of j omega, where omega is the frequency of the cosine, and we have to add in a phase angle to the cosine. So by doing those simple operations, we can get the output without having to do any convolution. We can get the output from the input. And I want you to notice that we found this output without having to do Laplace transform or inverse Laplace transform. It's simply a matter of multiplying the input by a constant and adding a phase shift. So we found the response to an everlasting cosine quite easily. What about a causal cosine signal? Can we use what we just learned to find its response easily? So here's an important result. Let's suppose the transfer function, h of s, is a Biot stable transfer function. In this case, we know the following, that the zero state response of this system to the input x of t equals cosine omega t u of t, that is the causal cosine, shown here in the figure. This response becomes arbitrarily close to the sinusoid y tilde of t equals magnitude of h of j omega times cosine omega t plus phi, where phi is the angle of the complex number h of j omega. It becomes arbitrarily close to the response to an everlasting cosine as t goes to infinity. Let me paraphrase the importance of this result. We can find the response to the everlasting cosine quite easily. We know that the response to the causal cosine will approach the response to the everlasting cosine after a transient dies out. So while we can't find the response to a causal cosine easily, we can still know what it will be after some time. We know that after some time, the response to the causal cosine will be the response to the everlasting cosine. And again, we can find the latter quite easily. Here is what is meant by this result. We'll put in a causal cosine input to a linear system. So this is x. The response to this we'll label y, and it's shown in blue in this graph. And what you'll note about y is that as time goes on, it'll approach y tilde, marked in red. Y tilde is the response to an everlasting cosine. So for a Bibo-stable system, the output will become a sinusoid at the same frequency as the input. The only difference, after some time, between the output and the input will be one of the magnitude or amplitude of the signal and the phase of the signal. The significance of this result is that it allows us to understand how a system behaves, how it responds to inputs, without having to do a lot of difficult calculations, say using inverse Laplace transform. If we're not terribly concerned about the transient, we can just find the response to the everlasting cosine. We know that the response to the causal cosine will approach this with time. Not surprisingly, the same sort of result holds for the causal sine wave input. That is, if we look at the response of a linear system to an everlasting sine input, and let's label that y tilde, we can find that response in the exact same fashion as we found it for the everlasting cosine. We simply take the input and we multiply it by a number. That number is the absolute value of the complex number h of j omega, where omega is the frequency of the sine wave. And then we also do a phase shift to the sine wave, and the phase shift is by phi, where phi is the angle of the complex number h of j omega. So the y tilde is a response to an everlasting sine input. Now, the response to a causal sine input will approach y tilde as time goes on, as long as the system is Bibo stable. Let me note that in this discussion, the magnitude of the input x of t was 1. If we plot x of t, it goes between 1 and -1. So that's how large the input is. The magnitude of the output, y of t, is the absolute value of the complex number h of j omega. So that's the amplitude of the output signal, y. So h of j omega is how much magnification the input signal gets when it passes through the system. And this is referred to as the gain. The gain is the amount of amplification of the input signal as it passes through the system. Now the gain here, which is the magnitude of the complex number h of j omega, is obviously a function of the frequency omega. At different frequencies, the system will have different gains. So at some frequencies, for example, the system might make the output 3 times bigger than the input, and at other frequencies, it might make the output 1/10 the size of the input. This is the nature of the amplification that a dynamic system gives to a sinusoidal input. The amplification is different at different frequencies. Now let me point out one very special case of the gain, and that is the gain at 0 frequency. So we take omega, we set it equal to 0, evaluate h at that value, take the absolute value of that number, and that is called the DC gain. It's how much amplification a signal at 0 frequency receives when it passes through the system. Now later on we'll have a whole presentation on DC gain. So we just discussed how for a sinusoidal input signal, the output will have a different magnitude than the input, and the ratio of their magnitudes is the gain of the transfer function at the frequency of the input. Now we'll look at the other difference between the input and the output, and that is they have a different phase angle. The input we'll be considering is the everlasting cosine, x of t equals cosine omega t. We'll refer to this as zero phase, since the phi that would appear in cosine omega t plus phi is 0 here. Now the phase angle of the output is the angle of the complex number h of j omega. We know the response to the everlasting cosine is y of t equals the absolute value of h of j omega times cosine omega t plus phi, where phi is the angle of the complex number h of j omega. So you see the phi for the input is 0 phase, and the phi for the output is the angle of the complex number h of j omega. When we plot the input and the output together, as shown here, you'll note that the phase of the output, y, is different from that of the input. For the case shown, phi is positive, and therefore the output is shifted to the left in comparison to the input. This case, where phi is positive, is referred to as phase lead. So we say that the transfer function has phase lead at this frequency. At other frequencies, however, phi may be negative, and at frequencies where phi is negative, we refer to the transfer function as being phase lag at those frequencies. In those cases, y would be shifted to the right. Let me close by summarizing what we've learned here. If we put a cosine signal as an input to a linear system at a frequency of omega, the output signal in response will also be a cosine signal. It will have different amplitude and different phase than the input, and the amplitude and the phase can easily be found from the transfer function. The amplitude will be the magnitude of h of j omega, where omega is the frequency of the input, and the phase will be the angle of the complex number h of j omega. So now you've learned some really important facts. If a system has a sinusoidal input, then the output is also sinusoidal and at the same frequency as the input. Moreover, we can find the output from the input merely by looking at the transfer function evaluated at the frequency of the input. The magnitude of this complex number gives us the magnification that the input receives when going through the system to produce the output. And the phase of this complex number gives us the relative phasing between the output and the input. How can this insight be used in engineering practice? Consider the example of a car moving over a bumpy road. If we know the frequency of the bumps in the road at the car's particular speed, we can figure out from the transfer function of the car's suspension what impact this would have upon the passenger. Since this transfer function would depend upon the stiffness and damping of the suspension, this gives us insight into how to pick the suspension so as to minimize the discomfort to the passenger. I hope you see the importance of this idea. In our next lecture, we'll be reviewing some basic facts about the magnitude and phase of complex numbers. This is an important preliminary for the discussion that will follow.